All right, welcome to AP Podcast 5.6. This is on KM Theory. And for most of you, this is going to be kind of a review because this is what tells us why things happen when we're dealing with ideal gases. So that, again, is the point when we're talking about ideal gases. In real life, okay, as I've got down here, it doesn't quite fit, but for those of us in AP chemistry, it's really not an issue. We deal with ideal gases, and so KM theory really helps give us a visual of what's going on. So let's get right to the points, and let's look at the first one. The particles are so small we can ignore their volume. So can you imagine a spot, and you've got all these little bitty particles, and what we say is they're so small their volume does not affect them. Unfortunately, we know that in real life gases do have volume, but for our purposes we're going to say that they really don't have a volume. Now another assumption is that particles are in constant motion and their collision cause a pressure, and that's definitely true. An example you'll see a lot this year is the good old piston. All right, and imagine some gases stuck in this piston here, and then right on the top we have some kind of pressure gauge with a little needle. All right, and as these particles are flying around in all different directions, they're causing a pressure. And because those particles are in constant motion, their pressure is constant. If you think about blowing up a balloon, the reason that balloon retains its shape is because all those billions upon billions of molecules are bouncing around in that balloon, keeping the balloon in its shape. And the only reason the balloon is going to deflate is when some of those particles escape, which is what our next podcast will be. On to part 3 of KM theory. Particles do not affect each other, neither attracting nor repelling. Now, we know that this is not true. What this says is that when a particle gets close to one another, there'll be no attractive forces, or there'll be no repulsive forces. So that is not true. Things repel and attract, and when they bump into each other, that's going to cause problems too. They're going to slow down, one might speed up, but again, we're not going to really worry about those little details. We're just going to say for the most part, there's no attraction or repulsion. So it's almost as if every single particle is an independent entity, not all by itself inside the, let's say, the flask. All right? And then last but not least, the average kinetic energy is proportional to the Kelvin temperature. That is super important because that means the faster it's moving, the greater the temp. So if things are really moving fast, their temperature is very warm. If gas particles are moving slow, then their temperature will decrease. Now, if you want to look at Appendix 2 in your book, and if you're into this sort of thing, this is beyond the scope of AP, you can see how they derive the ideal gas law, good old Pivnert, and how they give you the definition of temperature, which happens to be right there. Okay, so what this is saying is that the kinetic energy, and this is an average, equals 3/2 R, and this is a gas constant, times the temperature. So 3/2 in R, basically, you don't have to worry about that. So the kinetic energy is directly related to the temperature. So more energy, a greater temperature. Less energy, a lower in temperature. All right. Now, how can we use KM theory to solve some kind of interesting problems in AP? Well, I've already got this written out for you in hopes that I'm going to save a little time. And look at the kind of question that you might see on an AP test. Calculate the root mean square velocity of carbon dioxide at 25 degrees Celsius. Well, if you look at this equation right here, this little RMS, that's root mean square velocity, and that is of course on the equation sheet that we have that is given to us on the day of the test. And the important thing is to know what each one of those variables are and how those units work out. So let me just kind of briefly go over this. So it's 3 times R. Now the R we have here, notice it's 8.314 joules per Kelvin mole. That's important because with Pivnert we've been using 0.0821 joules per mole, or joules, not joules, atmospheres, liters, Kelvin, moles. Sorry about that little brain fart there. But whenever we use energy, or kinetic energy in this case, we want to make sure we use this R. And again, you guys know we always calculate energy in joules, so that hopefully will help you out. So we take that R constant and we multiply it by the temperature. Now notice it says up here it's 25 degrees Celsius, but of course we're going to switch it into Kelvin, right? And you know, if you forget that, look at that constant right there. There's a K right there. Okay, and then we're going to divide by the molar mass. Now this molar mass is a little different than what we're used to. If I were to look up the molar mass of carbon dioxide, I would get 44 grams per mole, right? But in order for our units to cancel, and I'm going to show you how that works in just a second, it's got to be in kilograms per mole. And that's kind of what I have down here. It's got to be in kilograms per mole. Okay, and the reason for that is we're going to define what a joule is in just a second. Okay, so instead of just taking 44 and dividing by 1,000, I just did 44 times 10 to the minus third kilograms per mole. So hopefully that is not too much of a confusing thing for you. So now I multiply those three numbers together. I divide by 44 times 10 to the negative 30. And I get this rather large number. And then I wrote out what the unit of a joule is. A joule is a kilogram per meter, kilogram meter squared per second squared. Now, those of you that are in physics or are moving on to physics next year, you will definitely figure that out, and you'll use those units a little bit later. But we really don't use them too often in chemistry, but in this problem, we need to be aware of that. Okay? Now remember, we're talking about a velocity, and again, this is a physics thing. Velocity is always going to be in meters per second. So watch how these units cancel, because it's pretty amazing the way it works. I've got a Kelvin on the bottom. I've got a Kelvin on top, right? I've got a kilogram on the top. I've got a kilogram on the bottom. I've got I've got a mole on the bottom and a mole on the top, and I'm going to be left with meters squared per second squared. However, look at this. Since I've got the square root sign, that's going to go ahead and cancel those squares, and I'm going to be left with meters per second. Okay, and we get 411 meters per second. So what that means is if I were to watch one particle of carbon dioxide floating around, let's say it's in a balloon or some kind of vessel, it would be moving around at 411 meters per second on average. Obviously, in a real-life situation, some are moving faster, some are moving slower, but on average, they're moving around at 411 meters per second. And that's pretty fast. So hopefully this will make sense. We'll work a couple of these problems tomorrow just to make sure that you have it. And if there are any questions, don't hesitate to ask at the start of class. See you later.